I think I'm recording.
Yep.
Okay, super. It's been a minute. So thank you everybody again for coming. We're going to be taking a look at Hubble Space Telescope data to see if there was gender bias. This is from a real study, and it had a real impact on policy. So it's kind of exciting stuff. So I'm going to share my screen. The Desmos link will also be available. For folks. Oops, sorry, that's my email. So this is the Desmos link, and if you're watching online, you can also go to that link. You can go to student.desmos.com and then just enter in that code ARA8VD. And the great thing about Desmos is that I'm going to show you a little bit as the teacher side so that you can see what I see, and then I'll turn it over into the student side.
Is this Desmos available for us to see after the demonstration? Okay, thank you.
Yeah, I'll make it so that it's like shareable, like you could copy it and make it your own if you wanted to. Yeah.
Thank you.
Yeah. So this is what I see. And so for me, especially during COVID, it was really helpful to know for those who were zooming in, or if I just didn't want to get too close to people, who is where. So each of these slides sort of lights up. It tells me where they are. The dot means that they've done something on that slide. And so I can also control what slides that they can see. And I could see, I could say like, oh, Karen, come join us on slide 3 or something like that to get kids to stay with everything. So I'm going to put it on the student side and I'm going to move your beautiful faces over here so I can see you. Okay, now I can see everybody. So over on the first slide, we're going to be taking a look at the Hubble Space Telescope data and gender bias. So we know from lots of research in education, including stats education and math education, that students have to understand not just the mathematics in order to engage, but they also have to understand the context. So if you ask them to do, I don't know, a problem about a Ferris wheel or something, even if they know all the number theory ideas that go into Ferris wheels, they won't really be able to access the problem if they don't know what a Ferris wheel is, if they can't imagine it in their head, which for adults, we don't really care, like for people who are really good at stats, it almost doesn't matter to us. We can just see the structure, even if it's talking about widgets. But for learners, it's really important. So this first slide, I'm going to ask you to just tell me, do you know anything about the Hubble Space Telescope, what it is? If you don't know anything, you can click on this link right here, and there's a little fact page so you can learn about it. And it'll take 1 minute. I put a video in, but probably we don't have enough time for the video. And then I'll include, there's a link to an NPR story that's 5 minutes long with the text too. So providing lots of different modalities for students to get some background knowledge about not just the math, but like what's going on in the scenario. So if you could tell me anything you know about the Hubble Space Telescope over on slide 1, that would be great. So over on the side, I'm just watching to see if everybody has had a chance to put something in so that I know if I'm going too fast or too slow. So it looks like most folks have been able to write something down. And yeah, it is a big floaty telescope out in space. So the fact that it's above the Earth's atmosphere means that it can take amazing pictures really far away because it doesn't have, like light pollution or the atmosphere kind of getting in the way of these pictures. And it goes super fast around the Earth. And the astronauts can actually go visit it even to sort of fix it. So it's been up in space for a long time. And it helps us take amazing pictures. So hop on over to slide 2, and we want to talk about who gets to use the telescope. So you might not know the answers to these, and that's okay. I'm just trying to get a feel for what folks know already. Can anybody use the telescope whenever they want, or do astronomers have to apply because there's only a certain number of hours available? Is it only open to US astronomers, or can it be any astronomer? Does a panel decide based on the quality of the proposal and which of these are true? There might be, all of them might be true, maybe only one of them is true. Before 2018, the proposals had the PI's name on them. That's the person that's in charge of the entire project. Before 2018, they were judged not just on the quality, but who wrote the proposal. And then before 2018, male PIs were disproportionately more likely to get their proposals accepted than female PIs. So take your best guess about which one of those you think are true. Click off the ones that you think are true, and we'll talk about that. All right, looks like almost everyone has had a chance to answer. So I'll tell you the answer. Astronomers have to apply to use it because there are so many people interested in using it, and there's only 6,000 hours available each year that can be used. Any astronomer in the entire world can apply, so that's kind of interesting. And a panel is deciding on the based off of the quality of the proposal. So there's a panel of scientists that look at each one. Before 2018, the proposals did have the principal's investigator's name on them. And when social scientists were invited to listen in on the panel, they found that the panelists were not talking about just the quality of the proposal, but they were talking about, well, this scientist, you know, he does really good work, and we really trust him to be able to use the time well. And so because they were talking so much about the well-knownness, I guess, of these scientists, they were kind of taking into account both the scientist and the idea and the proposal and the detail and the methodology. So that's true. And then we're going to talk about this last one right here, where male PIs disproportionately more likely to get their proposals accepted than female PIs. So we know from like we know that in UDL, Universal Design for Learning, we really want to highlight the big ideas and patterns. And so one of the ways that we do that in our class is using the GACE guidelines, thinking about statistics as a process. So what is the statistical inquiry process? And in each of my classes, it doesn't matter what we're studying. Maybe we're studying box plots, or maybe we're studying, you know, mean, median, mode, or something. We're always kind of going through this whole process of what's the research question and looking at a set of data. Often the study is one that already exists, but sometimes we collect data in class and then exploring the data, drawing inferences, formulating conclusions, and looking back and ahead. So we're always going through this, and this kind of helps students to sort of stay organized because they have this structure. So our research question is, are proposals submitted by female PIs disproportionately less likely to be chosen? The data we're looking at was compiled by Ian Neil Reed in 2014, and it's looking at cycles 11 through 20 of the proposals. And he identified the gender of the principal investigators for each of the proposals. So we're going to look first at cycle 11 only, and then we're going to look at all of the proposals together, partly because we want to see what's that impact on the sample size on our conclusions, and partly because the numbers are smaller. They're easier to make sense of. So over on slide 4, if you could join me over on slide 4. I'll wait for folks to get there. And Desmos, because I want to know what your first guess is. So over on slide 4, we have some of the data. So this is just cycle 11 data. A cycle is about a year. It's sometimes a little bit longer because of maintenance issues, but it's about a year. So in this small table, I've taken out the information about the men, because if I include the information about the men, the students want to usually compare men and women. Totally legitimate way to do this data analysis, but we usually don't have the tools to do that at that point in the semester. So what I'm looking at is I have the accepted proposals during cycle 11. There were 198 proposals that were accepted. Of those 198, 30 or 15% were submitted by female PIs. The total proposals that cycle were 1,078. If we looked at the total proposals, 19% of them were written by women, 205 proposals. So just looking at that data, what do you think? What's your guess? Do you think there's evidence that there's a gender bias in whether Hubble telescope applications by female PIs were accepted. So go ahead and click on one and tell me what you think. I'm going to take a second. Nice. So I'm just looking at what folks are writing because it helps me to understand what students are thinking about. So often students will say, well, oh, it should be 50%. And so you have to redirect them that like, well, or they'll say something like, well, women don't, there aren't as many women scientists or something like that. And so while some of that might be true, that helps us to zero in on what we're comparing. So yeah, it's true that women were less likely to put in a proposal, but even given that, they're less likely to have their proposal accepted, right? So only 15% of those proposals that were accepted were written by women. If there wasn't a gender bias, we would, and the proposals were of equal quality, we would expect it to be a little bit closer to 19%. But lots of people are saying really important ideas too, like maybe Stephanie or Nadi, is it Nadi? Do you think you could share kind of what you were thinking? If you're able to share, I don't know if you're in a spot where you could share.
Hi,
So
can you hear me?
yes, I can hear you. Yep,
Yeah, I go by Nadi.
Nadi.
Yeah, I was thinking, yes, there is a difference. 19% is 4 units higher than 15%. But like if you take a different sample of data, it would be different data, right? So we don't know this difference is statistically significant or not. That's what I was thinking. I don't know if a student would think in the same way, you know?
Yeah. And this is usually like the second lesson I would have done on sampling. Usually we do something like M&Ms or something
Yeah,
beforehand. But yeah, I agree with you. Like we don't know quite yet, like 15% is less than 19%. Could that just happen like just due to chance, right?
chance,
Yeah.
exactly.
Cool. All right. So over on slide 5, if you could join me over there. So we can think of these cycle 11 proposals as the population and the accepted proposals as a sample. So it's not a random sample, right? Because there's criteria and everything, but we can think of it as a sample and that it's a subset. And so like Nadine said, 15% is less than 19, but maybe they're close. Maybe that difference we could see just due to chance, or at least that size of a difference we could see due to chance. So maybe in the long run, if we had many cycles of data, the proportion of accepted proposals that are submitted by women would be the same as the proportion of all the proposals that are submitted by women. We're only looking at a small group. So first off, down at the bottom, just tell me what kind of sample is this? Is it a random sample or not a random sample? And then what's the correct way to write this using the notation? So UDL tells us that we need to help students decode mathematical notation. And what we've learned in our practice is that at Curry, you can't just do that once. You have to do it over and over and over again, help them to see the how to use that notation to be able to read the mathematics. So I'll give folks a minute over on slide 5. What do you think? What kind of sample is it? Thinking about it in this way. And then how might you use that notation? Right. So most folks are saying like the population, we're going to use that pi to be the proportion. I know other folks use different symbols. In our class, we use the Greek letters pi. And 19% because we're thinking about all the proposals as a population. We would say that pi is equal to 19% are women. And then p hat is used for sample proportion. And in the sample of accepted proposals, only 15% are women. And yeah, it's not a random sample, right? But we're wondering if we could see this difference just due to random chance. Like would a random selection give us the same size difference? It's kind of what we're asking. Okay. So over on slide 6, I just wanted to make one of these because I find them super helpful. And I'll show you what it looks like on the teacher end. So again, we're trying to decode some of this vocabulary for students. That's one of the things I keep saying is hardest for them. And you're going to make 2 groups. One is all about the alternative hypothesis, and one is about the null hypothesis. There's a card that kind of, sort of in layman's terms explains what the meaning is of the null hypothesis and the alternative. There's the symbols, HO and HA, or H naught and HA. And then there's the way we would write it in mathematical notation. So if you pick up these cards and kind of hover, they light up. And if you let go, they group. And you can ungroup them by taking the lower card. And if you group them, instead of just putting them super close to each other, then I can see on my end what you're saying. So I'm going to anonymize people so that you can't see their names. But if I go over to teacher, I can see who's actually grouping their cards and who hasn't yet. And if I click show correctness, it'll show me who's kind of basically got it right. And it'll light up things in orange if maybe one card is off or something like that. And I can zoom in on individual students' screens too and check the correctness. And this helps me because I don't like to spend a ton of time on vocabulary. So it helps me to quickly assess if we need to slow down or if most of the students got it and I just need to check in with a couple. So I'll give you a chance just to try out slide 6 so you get a feel for it, and then we'll talk about it. And then I'll show you how to use the applet, and we'll spend most of our time on that, kind of talking through that stuff. And for folks who are already done, I can show you too that you can write little notes to people. So, oops, I took off the anonymize, came off. I'll anonymize. So I can write a note that says, good job, or check, number 2 or something like that. And then they get it on their end too. And that's one way that I can help, like maybe over here, I might say, oh, check, you need to figure out the difference between those two cards. I see some cards still moving around, so I'm gonna hang out here so everybody gets a chance because I know can go really quickly. But if you want to poke over on slide 7 and start taking a look, you can do that. Okay, so it looks like the card moving is slowed down. So I'm going to show you what the official answers are. Often what I'll do is I'll actually put students together that might have gotten them right and wrong just to have them explain their ideas, looking out for students who maybe don't get a lot of opportunities to talk and be the expert. And I can do that because I can quickly see who has it right. But because we're on Zoom, I'll talk you through it. So I think most folks remember that the null hypothesis is H naught, alternative is abbreviated HA. And the null is the no effect. So there's no gender bias. In the long run, the percent of accepted proposals that would be submitted by women PIs would be the same as the percent of all the proposals that are submitted by women PI. And the same for the alternative hypothesis. Except that there is a gender bias in the long run. The percent of the accepted proposals that are submitted by women PI is less than the proposals of all the proposals that are submitted by women PI. And so If the null hypothesis were true, we would expect that the proportion of all the proposals that are women would be the same as the accepted proposals if we had the bigger data set, if we could do this forever. And in this case, we're doing a one-tailed test, and we saw in our actual data that it looks like maybe the proportion of accepted proposals that are women would actually be smaller. So we're going to use this one. Okay, so I'm going to show you how to use the applet, and I put links into the applet. But I've also written down the steps here in case I go too fast or you're looking at your screen and not mine. So if you click on the cycle 11 data, that's going to bring up a Google sheet. And I deleted the extra columns and rows and the extra spaces and the variable names so that you can just do Control A and then copy, or you can just click on and use Shift and your arrow keys to copy those columns that you want. If I found that if there's extra spaces, sometimes students put that in the applet and it gets a little confused. So, oops. And then the sampling from a finite population applet is linked in Desmos too. If you click there, clear out that existing data, put your cursor in the box and paste in the data. And then make sure you click Use Data, so it's actually using that data set. And then down where it says Choose Variable, select Gender. And then from there, you should be able to see out of cycle 11, what proportion of those proposals were submitted by female PIs right here. And once you get that so that I know people were able to figure out the applet, go ahead and put in the proportion that you found in that box.
Laura, can I ask a question?
Yeah.
When I was on the applet, like I'm still clearing the data and I feel like you just cleared it in one fell swoop. Can you
Oh, yeah.
show what you did?
Yeah, maybe I need to make it bigger.
Okay.
So I clicked on this clear button.
Oh my gosh. I take back my question. Thank you.
Yeah.
Actually, I'm glad I asked it.
Somebody
I
else,
did
right?
not see that.
Yeah.
Okay.
And then you can copy and paste. But make sure you click Use Data. That's the biggest thing that seems to trip students up. I don't know why. I'm looking over on Desmos to see. Sometimes I'll tell students, if you need help, you can also write, I need help. If you're too shy to raise your hand, and they'll write help in this box, and then I can go over. So we've got about maybe half the people that put in the sample or the proportion of all the proposals that were women. So I'm going to go through it one more time just so that you can see it. So over on the applet, the data is the cycle 11 data. If you click on that top link, it'll take you to a Google sheet. And then you can click on B and C, B shift C or B shift arrow C, and then copy. I'm doing Control C. Then when you click on the link that says sampling from a finite population, it'll bring you to this applet. You can click clear to erase all the default data, put your cursor in the box, and then Control V. Make sure you click Use Data. It will bring the data in. And then over down here where it says Choose Variable, change that to Gender, and then you can see the proportion of female PIs is 19%. Okay. Yeah, okay. Looks like most folks have got it or are moving on. Great. So thanks for your patience. I know that one of our pieces of feedback is, oh, it went so fast. So over on slide 18, so remember there were 198 proposals that were accepted in cycle 11. If you were going to take a sample of 198 proposals from that larger group of over 1,000 proposals, what proportion of them would you expect would be submitted by female PIs in that small sample? And do you think it'd be exactly that amount, or do you think it could vary a little? And if you think it could vary a little, what do you think it might be? So go ahead and take a guess over on slide 8. Nice. So lots of folks are saying they think that it would be 19% female, but vary a little. Some other folks are saying 38 proposals or 37, because if you took 19% of 198, that's what you would get. Oops, sorry, 37. But some folks are saying it's going to vary a little. So the great thing about the applet, and we've used them with mathematicians in our area too, is it like really makes you feel like physically how much something can vary. You might know it mathematically and be able to, calculate binomial distributions and everything, but when you witness it, it kind of gives you appreciation even as an expert for what that variability might look like. So over on slide 9, these are the directions for getting the applet to take a sample. So I'm going to go back to my tab. And if you go to that applet, there's a box that says show sampling options. And if you click on that, a whole bunch more options show up. So we're going to take a sample of a size 198 because that's the same as our sample. And our sample was those accepted proposals. I'm just going to take one sample to start. I think that really helps students see like what's happening. I'm going to click draw samples. So one thing they get mixed up is these two boxes. The sample size is how big our sample is. And so what this applet did was it took a random sample of proposals from the population, 198 of them, and then it calculated the sample proportion of, in that group, what percent of them the proposals were submitted by a female PI. So in this case, it's 22%. It's a little bit higher than that 19%, right? And then what's also happening is this third graph over here is going to keep a running record as you take more samples. So this is showing us that for this particular sample, 22% of them were women. If I drew another sample, if I click draw samples again, in that sample, I got 17% of the 198 randomly chosen proposals were women. So it's less than what I would have expected as the 19%. And we can see that it's plotted it over here. I can go back to the earlier samples too by clicking on them if I wanted to see where they came from. I should be able to. Something's going on. Okay. So go ahead and try that. Just do 1 or maybe 2 samples to get a sense of how that works. And then over on slide 10, tell me where your first sample landed. So my first sample was like 22-ish, 0.222. So it was here. And I don't know why it says explain your thinking. I tried to turn that off. But go ahead and put in your sample proportion, and it should create a graph for us, hopefully, that shows everybody's sample proportions and how they could vary. So that's over on slide 10. It's like so far we've got 6 folks who have entered in their data. I think we've got like 5 more people that are playing with the applet, so I just want to give them some time. So it looks like if we look at this graph, this is the beginning of our sampling distribution, right? It's the same as this third graph over here that we'll get in a minute. We've combined our data. So if I was to do this in class, usually we'll do one made out of sticky notes. We'll write it on a sticky note and they'll put it up on the board. And I could see that it looks like mostly people are getting between 0.15 and 0.25. So kind of hovering around what that population proportion is of 0.19% women. But some people are getting outside of that, right? Someone got somewhere between 0.25 and 0.3. So it's possible that we would get something unusual when we're taking a sample of 198 proposals. So over on slide 11, we're going to take multiple samples. Right here, let me make this a little bigger. So the directions are right here. Where it says number of samples on the applet, that's where you're going to change it to be 100 or 1,000. I usually start with 100 because it's easier to see each individual sample and then have students get to a total of 1,000 samples. And that usually they start to agree. At 100 samples, they might find differences between their graphs, but like anything above 1,000, they seem to sort of even out. So you're going to change that number of samples to be 100 or 1,000. And then I'll take a look at this graph in the bottom right. Each of these squares represents one group of 198 proposals. And if you go down to the bottom, it'll tell you what proportion of that group of 198 proposals were submitted by female PIs. I want us to just sort of take a look at it qualitatively first, like what's the smallest sample proportion that you get? What's the biggest sample proportion you get? Where does it kind of hover? Where's the mean? And then where's the standard deviation too? So this is the standard error because it's about a sample statistic. What is that? That's about how spread out this data is. And we're going to look at how that changes when we change our sample size. And then if you're able to see about how often it happens that we get a sample where we had 15% or fewer of them were submitted by female PIs, write that down too, because that's going to help us see how common our results would be due to chance. Okay, so I'll show you how to do that on the actual applet. Over here, the only thing I'm changing is number of samples. I'm going to change it to 100, 1,000, draw samples, and then take a look at your distribution and sort of what do you see? Like how spread out is it? What's the smallest? What's the largest? What's that standard deviation or that standard error? How often are we as low as what we got in our actual sample? And then tell me over on slide 11, and that will help me make sure I'm not going too fast. And of course, you could shout out if you have questions too. If you're like, I can't remember what you clicked on, can you do it again? Go ahead and unmute and shout it out. So it looks like we've got the majority of folks, it's like maybe 3 or so who haven't put in any data. So I'm going to move on, but again, just shout out if you want any help. So it looks like most folks are saying, yeah, it's clustered kind of near, you know, the mean was pretty close to the mean of the population proportion. And then if you do this a bunch of times, like 1,000 times, you'll start to see that it really settles down. Other folks were saying that it seems to go all the way from maybe 11-ish% all the way up to maybe close to 30%, that spread right there. So you can get a lot of different proportions when you're taking a sample size of only 198, right? Some folks even talked about that standard deviation right here. It should be around like 0.02 something. It seemed like most folks were getting. And then of course, if we did even more samples, we would start to have our distributions agree. So down here, it can get kind of hard to count how often we get something like our sample proportion or even smaller. So down here where it says count samples as, we can change it to less than. And then we would put in the 0.15 because that's what we got in our actual study. We want to see how likely is it we would get a value like this due to chance, even if we were just taking like random samples to figure out who to accept. And if you click count, it will tell you, in my case, I got out of over 1,000, that happened only 50 times. So this would be your p-value right here. How often would I get a result that's as extreme as what I saw in my actual study? But maybe it's not fair to assume that we would get fewer proposals accepted by women. Like maybe we want to be a little bit more cautious, and we can do a two-tailed test by clicking on beyond. So we expected to get 19% of the proposals would be women. We got 15%. That's a difference of 4%, as a lot of folks said online. If we went 4% in the other direction, I'm fudging a little bit, but if we went 4% in the other direction, that would be like 23%. And we could see, well, how often would we get like a ton of women just due to random chance? And students are able to see that it makes sense that that p-value would approximately double, right? Because we're looking at two different tails. And so in this case, that seems pretty frequent that we would get something as unusual as 15% that were women, just due to random chance, right? So if you hop on over to slide 12, you don't have to tell me about why to do a two-tailed test, but this is kind of walking you through the logic and how to actually do it on the applet in case you forget. But over on slide 19, using the two-tailed test, what do you think? Like, what would you conclude? That there is a gender bias, there isn't a gender bias, we don't have enough evidence. What do you think? So do your best guess, and we'll talk about that over on slide 13. About half the folks have made a guess over on slide 19. And give it like maybe one more minute. All right, it looks like it's settling down. So I agree with the majority. We don't have enough evidence. So a lot of times students will say this, there is no gender bias, but we don't know that to be true. We just haven't been able to detect it. And in fact, by looking at a bigger sample, I think that really helps them to understand that we just don't have enough evidence. It could be that the long run proportion is 15%, but it's just that it's possible that it is 19% because you could get 15% by chance. So it's that last one over there. So if you hop on over to slide 14, we only looked at cycle 11, and we're wondering, well, what would happen if we looked at cycles 11 through 20? So we're gonna, sorry, I just saw the chat, but okay, I'm not monitoring the chat. Sorry, I have so many windows open, but I'll go back through the chat and take a look in a minute. So we only looked at cycle 11. What if we had looked at cycles 11 through 20? So this table over on the right is all of those cycles put together. So we can see that there's a lot more total proposals. There's over 9,000 proposals. Over 2,000 were accepted. Almost 2,000 proposals from female PIs, and then the number of proposals that of the accepted proposals that were submitted by female PIs. So before I have students actually use the applet, I have them do some kind of like pre-planning. So it might be on Desmos or it might be something else so that I can make sure that they understand where the numbers are going and why. So over here on slide 14, I might have them sort of explain in words and then what number they're going to use. And then even translating into the applet, I might have a third column just to make sure that like we're actually using the applet in a way that makes sense. So in this case, pi is going to be the long run proportion of accepted proposals that are submitted by, I'm just gonna write women because I can't fit everything, but by female PIs. And in this case, under the null hypothesis, we would say that pi, we think, is equal to the total proportion of the proposals that are submitted by female PIs. So the nice thing about Desmos is it'll do the calculations for you. 1953 were all of the female proposals out of 9,000, over 9,000 proposals total. And then it disappeared. It should put in, let me try that again. 953 divided by the 9410 and it's going to be 0.2075. And then p hat is the sample proportion. So in this case, we're talking about accepted proposals that are submitted by female PIs, women's. And in this case, we're looking at all the accepted proposals that were written by women out of all of the accepted proposals total, because we're wondering what % of them are written by women. And I think I entered something wrong. Here we go, 2103. It's this number right here. And so 16%. So we're still seeing that discrepancy, right? These numbers are different because it's a different group, but we're still seeing a difference. And then this is a sample size. So this is the number of accepted proposals, because that's our sample in this case. And so that sample size is the accepted proposals. There it is, 2103. And then I might have them explain HO and HA and write it in symbols over here. So with the applet, and if you go on to the next slide, there's also written directions in case I go too fast. But the applet, I'll show you dynamically what we're going to do too. So I would leave this window open and open a new window with this applet so that you can refer back and compare your distributions and see how they're similar or different. This is the link to the applet if you want to use that direct link. And then the spreadsheet is the same, but you're going to click on the bottom tab, and this is all of the cycles from 11 to 20. So you can copy those and put it in the applet, and the second tab, applet. Remember to click use data, and remember to change the variable to gender. So you can see that the proportion now is a little bit higher of female proposal submitters. And then over here for the sample size, our sample size is bigger. It's going to be the 2,103. And we want to see how often. And what did I do? Number of samples. Oh, it didn't copy all the data. Sometimes my keys stick. We do 1,000 of those. Might crash because I'm on Zoom. There we go. Okay. And so we can look at, okay, how often do we get less than that 16% for women? And that's from 16% here, 16.79%. And we could see that in this case, that never happened. We can even do a two-tailed test. And that's never happening. And we could see that that standard deviation, that standard error is much smaller than, oh, I lost it, than it was before. And that range is smaller too, right? It's not going all the way down to 11, it's only going down to 18. And it's not going all the way up to 30, it's only going to 24. So yeah, the variation in the sample proportions is much smaller and the distribution is much more squished. You're not getting those unusual values. And so our p-value is going down there. Okay. So I'll give you a chance to try it out over on slide 15. There's directions in case you get stuck. And then maybe we can spend some time talking about, well, how do we conclude? Now, do we have enough evidence that we have a larger sample size? And then because we, like the last step is to look back and ahead, could this is what actually happened here was that the NASA decided to blind the proposals and they took the names off. And then the conversation was really much more about the quality of the proposal and the methodology and the idea. And they saw, of course, that women were much more likely to get their proposals accepted. And so we could look at that data too to see, did it work? And then have a conversation about where else would this blinding policy help address inequities. So maybe you don't have science students, but the same kind of thinking might support students who are in business classes and thinking about, well, gee, maybe we should take names off of resumes when we're hiring or something like that. Okay. So I want to give you a chance to play and also ask questions and be like, I don't know what to click on and call out. So I think I'll open it up for questions there, or if you want to walk through one more example or anything like that. And I'm trying to stop my sharing. Okay, if I stop sharing, the green box is gone.
Yes.
Yeah.
Yeah, thank you. All right, so I'm going to check the chat to see if there's any other questions, but also call out, or if you want me to go through something again, you can say that, and I can walk through something again. So Soma, did I have a typo where I said as or more extreme?
Oh, I was just asking because, because the p-value looks at the tail probability. And so I sometimes struggle with my students getting mixed up as to the probability at that point, as opposed like the 12% was that or more, right? Or like farther out, I mean. So sometimes I think
Yeah.
it gets kind of wordy, but how do you get around that wordy part to have them understand that, this is not as unlikely because there's so much more beyond it. And then, it is a technical difference between being at that point, the probability at that point versus the probability of that point or beyond. So yeah, I was wondering if you have a less wordy way to
Yeah,
still
no.
say the technically correct thing. Yeah. Because
Yeah.
usually I put those multiple choice questions and they just pick the one that's the longest because they're like, yeah, she's probably wanting me to pick this because it's the wordiest response.
Yeah, I think that's a frustrating thing, is this tension between like technical,
Yeah.
because we're drawn to the technical so that we're 100% right. But then, like, even when I went back through these slides, I kept saying, like, what percent are women? And I'm like, well, it's not what percent are women, it's
Right.
female PIs. And like, is it even, should I say female or women? And yeah, then it gets really wordy, right? Instead of just the short
Yeah.
men. So I don't, and I also struggle with the two-tailed test, getting them to understand, like, well, why would we look at the 24%, right?
Yeah. Yeah. And then interpreting those p-values are a pain because then you have to say this much or more extreme. And then more extreme is not just one side, it's the other side as well.
Yeah. Yeah, it's tough. I like Nadi has a good point about statistical significance and practical significance. And we do, I think it's in the ISI book, the one about wearing red or blue and whether or not that helps you win. And it's a huge sample size, so you get statistical significance, but it's like such a tiny difference between whether red helps you win or not, that's when we talk about statistical versus practical significance. That, I mean, I guess it's the Olympics, so it's a big deal, but like I wouldn't do anything about it. Like, I guess you could very easily just flip a coin, but if it was, I don't know, a kid's high school game or something, like, I think whoever got there first gets the red jerseys, right? But yeah, that's when we talk about it. But it's an interesting question, right? Like, is 4% practical? I mean, for that scientist, right, that gets to get in, it is, right? It's a big deal. You get to use the Hubble Space Telescope, and then we get more ideas from different kinds of people instead of the same stuff over and over again. No. Nadia, do you ever talk about statistical significance or practical significance?
I actually do, depending on, at the end of the hypothesis testings, I want them to learn that, don't just rely on statistical significance. I bring some examples sometimes, look at the sampling distribution, look at its spread, how you can see compared to the claimed value and the sample value. Like if you compare those two, do you see actual difference? Like I use that IQ score example sometimes. Sometimes I use in a business statistics class, I talk about, profits. It's another example I use. compared to the thousands of money you get from credit card holders. If you compare the profit difference that you found is like $10, do you think it would make any difference? Even though that difference was practically, even though it was statistically significant due to large sample of data.
Yeah.
And I also, used the distribution of sample mean or sample proportion to show the effect of sample size, why it is still statistically significant, although practically it doesn't seem to be different.
Yeah, it's kind of that looking back and looking forward part, right? Like now that we know this, does it matter?
Mm-hmm.
Yeah.
Exactly.
I use that to also talk about how important the context is. Like you said, right? It depends on the context. And there is an example we do in class, which is looks at like the difference in time. And, if it's the Olympics, maybe it matters. But if it's about, I give them the example of if it's just, the pasta timer, it probably doesn't matter how many microseconds or milliseconds or seconds it goes over. So how important the context is
Yeah.
to making that decision of practical significance. But the statistical significance is kind of, it doesn't so much depend on the context, right? It depends on the numbers itself.
Yeah. Yeah, and you have to use like your own knowledge about your field, right?
Mhm.
No, that matters, yeah. Alan has in the chat that some people are in favor of increasing diversity. Are you against blind auditions? That's interesting. I can't wait to read that.
The first time I heard about blind auditions being helpful, I was very persuaded, and I'd have to say I still am persuaded, but not everyone is persuaded. To summarize the New York Times article, they said blind auditions have been great for women musicians. They have not been great for musicians of different races.
I wonder too what students would think about like blind grading, because you can turn off in Canvas, you can turn off the names while you grade. Like would it be more fair, or would it be, because you also think about a student's growth sometimes, right, when you grade. So like I wonder what they would want, and that might make it one of the things for UDL is making things relevant, right? And so I think Hubble Space Telescope is relevant and impacted, and my science students do too, but how could we make it relevant for them that shows like the same structure is kind of at work?
Laura, I have a question just out of curiosity. Do you use or have you used Desmos in an in-person class?
Yeah.
Yeah.
I use it in not all of them, but in stats because it helps me. There's like always a subset of really quiet students that I can't get information out of. We have a lot of students with social differences. And so that helps me to make sure like I'm paying attention to everybody. So we use it a lot.
And so are you in a computer lab then when you're teaching?
No, they have computers with them.
They have a
They can do them on their phones too. It's not awesome on the phone. But we just bought these big tablets. They're like this big called flip charts. And so if they don't have their computer, then they can we have like somebody driving the big tablet, and so they can kind of all talk about it. And so if they only have their phone, I'll put them on the big tablet so that they can, because it's so small, on their phone, they can't really like draw very well on their phone.
Thank you.
Well, thanks for hanging out today. I'll hang around in case you want to talk about anything individually. We're going to post the slides, the Desmos slides, and all the materials on the website, which is, I should put the website link in there. Okay. Here's the website link where the Desmos slide link will be, and the Word document that's like the full thing that I will usually use with students if we don't do Desmos. And then links to like the NPR story and stuff too, in case you want to refer back to them. It'll probably take a day or so to get up there. Otherwise, have an awesome afternoon.
Thank you.
Thanks for coming. Stop recording.